Hello dear students, we are back with another lecture on graphical solution of LPP. So till now whatever problems we had done, the feasible region that we had obtained was a bounded region or say finite region, right? But there are problems where the visible region can be unbounded also. So let us have a look at those type of problems. So here I have taken one minimization problem. Minimize z equal to 5x1 plus 6x2 subject to the constraints 2x1 plus 3x2 greater than or equal to 1, 3x1 plus 2x2 greater than or equal to 1, and then x1 is less than or equal to 4 and x1 x2 greater than or equal to 0. Okay, so let us try to plot the straight lines. So in the solution what we'll write, we plot the region bounded or described by the given constraints. Okay, described by the given constraints. Okay, right, we plot the region described by the given constraints. So what are the constraints? So let us write it. 2x1 plus 3x2 greater than or equal to 1. Okay, that is x1 by 3 plus x2 by 2 is, I have to modify it a little bit. This was 6. Okay, even if it comes with 1 you can do it, but okay, that will require x1 by half and x2 by 1/3. Okay, so you have to do it that way. So here actually I wanted 6 here, so just please make that mistake, correct that mistake. x1 by 3, x2 by 2 is greater than or equal to 1. Okay, this is one constraint. Another constraint is 3x1 plus 2x2 is greater than or equal to 6. So that is, I convert it to this intercept form. It will be x1 by 2 plus x2 by 3 is greater than or equal to 1, and the other one is x1 less than or equal to 4, so I don't have to convert it to this intercept form. So we can plot these constraints, right? So let us plot these constraints and see what happens. Okay, so this is 1, this is 1, right? So this is your x1, this is x2 axis. So you have to mark everything like that, and you have to mark the points also here. Say I take 1 as this, 2, 3, 4, 5, 6. Okay, so it's always important that this markings should be equal. Okay, always. So better do it with a scale or compass. So here I am doing it manually, so there may be some mistakes as well, right? So these are the markings. This is the point 0. Okay, so this is 1, 2, 3, 4, 5, 6. Okay, also 1, 2, 3, 4, 5, 6, like that. Okay, so first one is x1 by 3 plus x2 by 1, x1 by 3 plus x2 by 1. Okay, so this x1 by 3 plus x2 by 2. Okay, so the curve will be something like this. Okay, so this is 1. Another one is the next one, x1 by 2 and x2 by 3. Okay, x1 by 2 and x2 by 3. It's not the perfect one, so let me draw it nicely. x1 by 3, x2 by 2. Okay, just let us try to rotate this, if it gets rotated or not. It's difficult to rotate this. Okay, so today I am successful in rotating. Okay, so almost it's x1 by 3, x2 by 2 is greater than or equal to 1, and the other one was x1 less than or equal to 4. So x1 equal to 4, we will draw it for x1 equal to 4, and then we will mark. Okay, so these are the lines. Now let us see what happens for the first constraint. X1 by 3 plus x2 by 2 is greater than or equal to 1. So 0 0 doesn't satisfy this, so that means the region is away from the origin. Okay, this way the region is towards this. Okay, for the first one, region is towards this. For the second one, the region is towards this. Okay, origin doesn't satisfy, right? So the region is towards these things. And for the third one, x1 less than or equal to 4, so the region is towards this. Okay, so what is the feasible region? If you can identify together with the non-negativity constraints, the feasible region is something like this. Again, this region is the feasible region, the region that is common to all the constraints. Okay, so this region, if you see carefully, it's the feasible region. So it goes beyond, it goes towards this. Okay, so it's unbounded, there is no upper limit. Okay, so the feasible region here is unbounded, right? So the shaded region, so let us name it, something like, let us start naming from here, say A, right? Then this will be B. Okay, so these are the points, this point, then this one, C, okay, D, okay, and say somewhere here E, etc. Like that. So there is no upper bound. Okay, so we are able to draw the feasible region. So here the feasible region marked by the points A, B, C, D, E. Okay, E is actually unbounded, Okay, so the region is unbounded, right? So next step is what we try to find out an optimal solution for this particular problem. So for that, what do I need? I need the cost function. Okay, so the cost function is this 5x1 plus 6x2. Okay, so we plot the cost line. We plot the cost line for z equal to 30. Okay, 5 and 6, the LCM is 30. That is 5x1 plus 6x2 is equal to 30. Okay, why we have taken 30? So that it's easier for us to draw the line. Okay, you can take 1 also, no problem, but you have to draw the lines accordingly. Okay, so it will be one of the parallel lines, x2 by 5 equal to 1. Okay, so let us try to draw this cost line. Let me draw it in a different color, say black, x1 by 6 and x2 by 5. Okay, so the line is somewhat, line is somewhere here, x2 by 5, right? Okay, so this is the line, the cost line. Okay, for z equal to 30. Next, what we do, our idea was we have to move the cost line parallel to itself. Okay, in such a way that for a minimization problem, it should be at a minimum distance from the origin. For a maximization problem, it should be at a maximum distance from the origin. Okay, so if this particular problem is a maximization problem, in that case we have to move the cost line this way. So you see, we keep on moving, it will never cross the feasible region. Okay, because the feasible region itself is unbounded. Okay, so the line is infinite length, so it's actually here you can see the finite part only. So the line is actually infinite, it goes on. Okay, it goes on. So if it is a maximization problem, this particular problem will have unbounded solution. Okay, that is, you cannot find the optimal solution. Means you cannot say which one is maximum, you cannot say this position is maximum, there are higher maximum positions also. Okay, so in that case the solution will be unbounded. But here the given problem is a minimization problem, so we move it in such a way that it comes to a position which is nearest to the origin. Okay, so if you see nicely, if I move it this way, so it is still inside the feasible region, right? So still it is inside the feasible region. Now when it passes through the point B, this is the last point in the feasible region. There are no other points below this point B, right? So at this position it is nearest to the origin and lies inside the feasible region. Okay, if it is somewhere here, it is not nearest, because I can move it towards the origin again. So when it passes through the point B, it is actually at a position where it is nearest to the origin. Okay, so we will write our answer accordingly, right? So we move the cost line, parallel to itself, till it reaches a position in the feasible region, where it is nearest to the origin, because it's a minimization problem. Okay, so it should be nearest to the origin. Okay, it should be nearest to the origin, right? But what we see is that at that position it passes through the point B only of the feasible region. Okay, it doesn't pass through any other point. So at that position it passes through the point B of the feasible region. But now what is the point B? B is the intersection of two lines, right? What is B? B is the intersection of these two lines, 2x1 plus 3x2 equal to 6 and 3x1 plus 2x2 equal to 6. Okay, but B is the intersection of of 2x1 plus 3x2 equal to 6 and 3x1 plus 2x2 equal to 6. Okay, so we have to find out the intersection of these two. Okay, so it's very easy to find out. Just solve it, multiply this one with 3, multiply this one with 2. Okay, and then so this will be 6x1 plus 9x2 is equal to 12, and this will be 6x1 plus 4x2 equal to, this was 18, this was 12. Okay, so if you just subtract these two equations, just simultaneous equation. Okay, so it's 5x2 is equal to 6, so x2 is actually equal to 6 by 5. Okay, and so x1 is equal to 6 minus 2x1 equal to 6 minus 3 into 6 by 5. Okay, so that is actually 30 minus 18 by 5. So what is that? 12 by 5. So that means x1 is actually 6 by 5. Okay, so your solution is optimal solution. Okay, optimal solution is x1 equal to 6 by 5, x2 equal to 6 by 5, and minimum value of z is equal to 5x1 plus 6x2. That was the objective function. So it's 5 into 6 by 5 plus 6 into 6 by 5. So it's actually 6 plus 36 by 5. Okay, so whatever it is, that's the answer. So 5 6 30 66 by 5. Okay, so there is the minimum value of the objective function. Okay, so that is how we can solve it. So you can try the same problem with maximization. Okay, so let us try that, the same problem with the maximization part. Okay, say this one, let us try this with the maximization. Maximize z equal to this one, subject to the same constraints. Okay, so of course our this EA part, that is called the diagram will be similar to this, right? Diagram is exactly similar, but the difference is we move the coastline parallel to it till it reaches a position in the feasible region where it is, instead of nearest, it will be farthest from the origin, where it is farthest from origin. Okay, but that position doesn't exist. Okay, but this is not possible. Okay, this is not possible as the feasible region is unbounded above. Okay, as the feasible region is unbounded above, since as you keep on moving the coastline away from the origin, it remains it remains in the feasible region. It doesn't go beyond the feasible region, because the feasible region itself is unbounded above. Okay. Unbounded above. So in this case, the LPP doesn't have any optimal solution. It has a solution. It has infinitely many solutions. You take any point here, it's a solution. Okay, but it doesn't have optimal solution. We cannot say for which position it is maximum. Okay, is unbounded above. So the given LPP does not have optimal solution, or has an unbounded solution. In this case, we also say has unbounded solution. Okay. Has unbounded solution. Bounded solution. So that means you can make the value of the objective function as large as possible. Okay, so this is the value of objective function can be made as large as possible. Can be made as large as possible. Okay, that is the meaning, right? So let us try another problem where we will take something different. Solve this. Say maximize z equal to let us try with the same function only, 5x1 plus 6x2 subject to. So now I'll change the diagram a bit. Okay, so that we can get some idea. Okay, so this is let's say maximize z equal to this, subject to the constraints, say 2x1 plus, let us take one from the textbook. It's difficult to construct the unbounded case. Just let me take the help of this textbook. Graphical solution, unbounded. This problem already we have done, unbounded. Yeah, let me try this problem. Yeah, this table problem, say x1 plus, let's try this, x1 plus maximize z equal to minus x1 plus 3x2. Okay, subject to the constraints, subject to these constraints, say x1 minus x2 greater than or equal to minus 1. Okay, and this is what, minus 0.5 x1 plus 1.5 x2 is less than or equal to 3, and x1 x2 this is greater than or equal to 0. Okay, so let us try this solution for this one. Okay, so let me rewrite this constraint. So we the writing is exactly same, just like the previous one. We plot the region described by the given constraints. Okay, so what are the given constraints? I can write it this way: x1 by x1 minus x2 greater than or equal to 1. So if you divide it by minus 1, this sign will change. x1 by minus 1 plus x2 by 1 is less than or equal to 1. Okay, this one. And then 0.5, so it's actually half, and this is 3 by 2. So I can write this one can be written as minus x1 by 2 plus 3x2 by 2 is less than or equal to 3. Okay, so this is what is happening. So this is actually x1 by minus 6 plus x2 by 2 is less than or equal to 1. Okay, so these are the two constraints. So let us try to plot this. Let us try plotting this. Okay, so this is one, and this is another one. Let me make the markings here. So 1 2 3 4 5. Okay, 1 2 3 4 5, they're not proper. Okay, so we have this x1 by minus 1, x2 by 1. Okay, x1 by minus 1, x2 by 1. So x1 by minus 1 is somewhere here, x2 by 1. So the line will be joining this two. Okay, line will be joining this two. Okay, so it's something like this. This is one line. Another line is x1 by minus 6 and x2 by 2. Okay, x1 by minus 6, x2 by 2. Minus 6, so I have to draw it this way actually. 1 minus 2 minus 3 minus 4 minus 5. So I should have drawn it. Okay, minus 1 minus 2 minus 3 minus 4 minus 5. Say minus 6 is somewhere here. x1 by minus 6, x2 by 2. Okay, so it will pass through this somewhat like this. Okay, so suppose this is the line. Okay, now I have to plot the region where this is happening. Okay, so the first one is x 0 0 satisfies this, the first constraint. So the region is towards this. Okay, for the first one, the region is towards this, towards the origin. Okay, means the region lies where the origin lies. Okay, so for the first one it is this. For the second one also origin satisfies, so our region is again towards the origin. Okay, so if we see nicely, what is the common region? Okay, which region is common to both the regions? Okay, so you can see it very easily. This region, this particular region is common to both the regions. Okay, so this region is also actually unbounded region. Okay, so the region here itself is also unbounded. Now let us plot the cost line. What is the cost line? Minus x1 plus 3x2. Okay, so we plot the cost line for minus x1 plus 3x2 equal to 3. Okay, so that is x1 by 1, x1 by minus 3 plus x2 by 1 equal to 1. Okay, let us plot this. X1 by minus 3 and x2 by 1. Okay, so it's something like this. Oh, sorry. Control Z. X1 by minus 3 and x2 by 1. Okay, so this is the cost line. Okay, and since it's a maximization problem, we have to move it in such a way that it remains farthest from the origin inside the feasible region. Okay, so let us see how. So obviously we should not move it this way downwards, because it will go towards the origin, means it will go nearer to the origin. So I have to move it away from the origin. So if you see, can I keep on moving it in such a way that it goes away from the origin? In this diagram it seems that it happens, but here actually this line extends to infinity. Okay, so will it ever cross? These two lines are actually not parallel to one another, right? So whatever line you draw, it is ultimately going to cut this particular black line at some point, and this region is itself unbounded. So there is no bounded solution here. Okay, so we will write the same thing. The feasible region is unbounded here, and as we move the cost line parallel to itself, it never reaches a point where it is farthest from the origin, because it keeps on moving, right? So the problem cannot be said to be completely in order, as there are solutions with very large videos. So far as discussed. Okay. Right. So which extension it gives z equal to 6 and is therefore optimal solution. Okay. Whether this line coincides with something. See, the drawing of the diagram is that's why it's very important. Okay, what is one of the constraints? This particular constraint is what, minus x1 plus 3x2 less than or equal to 6. See, why I told you that drawing the diagrams is very important. One of the constraints is minus x1 by 2 plus 3x2 by 2 is less than or equal to 3. Okay, so if you simplify this is actually minus x1 plus 3x2 is less than or equal to 6. Okay, and you compare this objective function, right? So the any cost line is actually parallel to this one of the constraints. Okay, parallel to the boundary of one of the constraints. So in the diagram that I have drawn, since the markings are not proper, it doesn't seem that it's parallel. Okay, so that is why the markings are very important. Let us try to draw the same thing in this GeoGebra software. Okay, so that it's easier for us to understand that whether these two lines are how these two lines are coinciding with one another. Okay, so let us try it very quickly. That is why I told you that in your exams also you have to draw the diagrams very properly. Okay, so let us see. Here the markings are there, but I have to move it a little bit. How to move this? Minus 6. The axis. Okay, just wait. Settings. Yeah, graphics, x-axis. Yeah, minimum x-axis. Let me just make it say minus 8, something like that. Okay, and then let me close it. Save settings. Okay. Yeah. So now we can draw it. This line through 2 points. Okay. The first one was through minus 1. The first one was through this one, minus 1 and 1. Okay. First one was through minus 1 and 1. So let us try it. Minus 1 to 1. Okay, minus 1 is this one. Answer. Okay, so settings close. Okay, so let us try drawing it now. Just yeah. Okay, so if I minus 1 and 1. Okay, so this is one line. Another line was through max x equal to minus 1 to, the other line was through minus 6 and 2. Okay, minus 6 and 2. So let us try to draw it. Minus 6 to this. minus 6 and 2. Okay, this one. And another line is the cost line. Okay, the cost line is minus 1 and 3. Okay, so it's minus 3 and this 1. Did I draw it from minus 1, minus 2, minus 3, minus 4, minus 5, minus 6? Oh, sorry, minus 6 is somewhere here, I think. Yeah, this is minus 6. Okay, right. So now we can see this is the cost line. Let me just change this color. Okay, so this is the cost line. Okay, now it's okay. So the feasible region was this side, feasible region, and if we move the cost line, see, parallel to itself. Okay, if we move it parallel to itself, okay, parallel line. Okay, this is the line, and yeah, so see, if we move it parallel to itself, it ultimately coincides with this particular line. Okay, one of the boundary of one of the constraints. Okay, so here, even though the feasible region is unbounded, we get something different here. Okay, even though the feasible, so here let me draw it properly. This particular line, it actually will be a parallel line. Okay, so this line, this particular line will be a line which is parallel to this one. Okay, minus 3 to 1. Okay, so something similar to this. Okay, so if we move it this cost line parallel to itself, it coincides with the constraint. Okay, so so here we have actually, even though the feasible region is unbounded, we have actually reached the boundary of the feasible region here. Okay, so even though the feasible region is unbounded, we have an optimal solution here. Okay, so that was what I was trying to focus on. Okay, in the earlier case, the feasible region was unbounded, the solution was also unbounded. Okay, but in this particular case, the feasible region is unbounded, but the solution is bounded. There is an optimal value of z. So don't go by the misconception that whenever the feasible region is unbounded, the value of z will not be optimal. Okay, the value of z can be optimal. It all depends on the constraints. Okay, so as we move the cost line parallel to itself. Okay, parallel to itself, it coincides parallel to itself till it reaches a position in the feasible region where it is farthest from the origin. Okay, till it reaches a feasible position in the feasible region, where it is farthest from the origin. It is farthest, okay, from the origin. Okay, it coincides with the line, this one, minus x1 plus what was that, x1 by 6 plus x2 by 2 equal to 1, right? This was the line, coincides with this line. Okay, which forms the boundary of the feasible region, of the feasible region, of the feasible region, not the boundary, there are various boundary, forms a boundary, which forms a boundary of the feasible region. Okay, and at this position it is farthest from the origin. So any point on the line, but there are several restrictions. Any point on this line is a solution, provided this intersection, okay, is greater than the x coordinate is greater than this point of intersection. Okay, so what is the point of intersection? Let us try to find out. So any point of the line okay, let us name it somewhere, say A, say X. So it goes this way, AX continued of the ray. So this is called a ray because so any point of the one endpoint is known to us, so let us name it as ray. Any point of the ray AX, okay, AX gives optimal solution. Okay, optimal solution. Okay, so let us find out what is the point A. A is the intersection of intersection of two lines. What was that? One is this minus x1 plus 3x2 equal to 6, and the other one is minus x1 plus x1 equal to 1, right? Minus x1 plus x2 equal to 1. So that is, if you solve this, or we can write solving, what do you get? 2x2 or 4x2 equal to 7. So that is x2 is equal to 7 by 4. And so what is x1? x1 is 7 by 4 minus 1. Okay, so that is 3 by 4. Okay, so maximum value of z, what is maximum value of z? It will be minus x1 plus 3x2, right? So this is minus of 3 by 4 plus 3 into 7 by 4. So it's 21 minus 3. 21 minus 3 is 18. 18 by 4. 18 by 4. Okay. Oh, sorry, I made a mistake here. I have to subtract this 2. So 3x1. So this is actually 2x2. This is 2x2 equal to 5. Okay, so x2 is actually 5 by 2. Please make this correction. X2 is 5 by 2, and x1 is actually x1 is x2 minus 1. x1 is 5 by 2 minus 1, that is 3 by 2. Okay, so your maximum value of z, equal to minus x1 plus 3x2. So what is that? Minus of 3 by 2 plus 3 into 5 by 2. So 15 by 2. Okay, so it's 12 by 2, that is 6. Okay, so optimal value of z is 6. So this is the difference between this problem and the earlier problem that we did. Okay, so here the feasible region is unbounded, but the solution is bounded, right? Z has an optimal value, and in the earlier one the feasible region is unbounded, solution is also unbounded. Okay, so there can be several cases, right? So almost we have done everything about graphical solution. So the other things you need to practice. I'll give you some more problems in the Google Classroom. You can just practice. So next day we'll take up the convex sets and their properties. Thank you.